Neurological and psychiatric disorders affect more than 3 billion people worldwide and remain among the leading causes of disability and disease burden. However, despite decades of research, developing effective treatments for these disorders continues to be a slow, costly, and often unsuccessful process. In fact, more than 90% of compounds that show promise during preclinical animal studies ultimately fail during human clinical trials. As a result, researchers are increasingly exploring new approaches that can improve the efficiency, accuracy, and ethical considerations of drug discovery. One of these approaches includes the use of artificial intelligence and computational modeling in behavioral neuroscience and preclinical drug discovery. Here, we investigated whether AI based computational models can serve as effective alternatives to animal testing and what limitations may prevent them from fully replacing traditional animal models. To address these questions, we conducted a narrative literature review using peer-reviewed studies obtained from databases including PubMed, ScienceDirect, Frontiers, Google Scholar, and PubMed Central. We focused on studies examining artificial intelligence, behavioral neuroscience, drug discovery, animal models, reinforcement learning, and generative adversarial networks. Particular attention was given to research evaluating both the benefits and limitations of these computational approaches. Our review focused on two major AI methodologies currently being used in behavioral neuroscience: reinforcement learning models, or RLs, or generative adversarial networks, known as GANs. Reinforcement learning is based on the way organisms learn through rewards and punishments. Within this framework, an animal makes decisions, receives feedback from its environment, and gradually adjusts its behavior to maximize positive outcomes. RL models are used to investigate decision-making processes, reward sensitivity, learning patterns, and behavioral adaptations associated with neurological and psychiatric disorders such as depression and addiction. These models allow researchers to move beyond simple behavioral observations and instead quantify cognitive processes such as motivation, reward learning, and expected outcomes. Researchers can then use this information to examine how potential treatments influence behavioral and neurological functions. GANs consist of two competing neural networks: a generator that creates synthetic data and a discriminator that evaluates whether the generated data resembles real experimental data. Through this process, GANs can produce highly realistic datasets that replicate biological and behavioral outcomes. Within drug discovery, GANs can be used to generate synthetic toxicological and physiological data, predict biological responses to drug exposure, and identify promising therapeutic compounds before extensive laboratory testing begins. Our findings suggest that both RL and GAN-based approaches offer significant advantages for behavioral neuroscience and drug discovery. These technologies can process large amounts of data, identify patterns that may not be apparent through traditional analysis, predict treatment outcomes, and improve experimental efficiency. They also have the potential to reduce costs, shorten development timelines, and decrease the number of animals required during certain stages of research. However, our review also revealed several important limitations. One major challenge is that behavior is inherently complex. Real-world behavior is influenced by numerous factors, including emotions, stress, and physiology. RL models often simplify behavior into reward-based calculations, making it difficult to fully capture biological and psychological influences. Similarly, GANs are highly dependent on the quality and diversity of the existing experimental data used to train them, and may therefore inherit biases, inaccuracies, or limitations that were already present within the original research. As a result, AI-generated predictions may appear convincing while failing to accurately represent the underlying biological processes. Another important limitation is that both RL and GAN frameworks rely heavily on pre-existing datasets, many of which originate from animal studies themselves. Consequently, these systems currently function as tools to enhance animal research rather than completely replace it. Furthermore, computational models struggle to replicate whole organism physiology. Drug responses are influenced by complex interactions involving metabolism, immune function, toxicity, and much more. These biological systems remain difficult to fully model computationally, limiting the ability of AI to independently evaluate treatment safety and effectiveness. Overall, our findings suggest that artificial intelligence is not yet capable of replacing traditional animal models in behavioral neuroscience and drug discovery. Instead, its greatest value lies in its ability to complement existing research methods by improving data analysis, generating new hypotheses, identifying promising therapeutic targets, and enhancing experimental design. The future of drug discovery is therefore not defined by a choice between artificial intelligence and animal research, but by the integration of both.